Good afternoon, everyone. Today I'm here to talk about our research paper on developing immersive VR experience for visualizing cross-cultural relationships in music. It's an AI approach to building interactive human-computer interaction in the field of music information retrieval. I'm Kaustuv from the Music and Sound Cultures Research Group at NYU Abu Dhabi. So let's get to the topic. So what's the relevance? So it's basically visualizing cross-cultural music similarities. First one is, of course, digital archiving, where we have a well-indexed collection with rich metadata and a multi-way searchability. Then community engagement. We want to make interactive interfaces for dissemination of the cultural heritage. Of course, it can also act as a compositional aid and pedagogy and evaluation for these music cultures. And finally, research on ethnomusicology, where we want to find out cross-cultural similarities, interactions, and patterns. And of course, our main focus will be on music similarity through audio analysis, machine learning, and visualizations. So the outline for this talk will be as follows. So basically, the approach is to combine data and knowledge-driven approaches. So first, I'll talk about setting the stage, where we come from, then corpora and audio processing techniques, discussing few of the experiments and results, and then the final core topic of this talk with respect to this conference, the visualizations, the VR, and finally concluding with some remarks and future work. So, setting the stage. And this is to basically say the goal and scope of the MaSC, that's Music and Sound Cultures Research Group. So who we are MaSC at NYU Abu Dhabi. We are a bunch of researchers, both experienced professors. I am a postdoctoral associate and student researchers, and there are collaborators working on music-related problem, computational ethnomusicology. And this is the introduction for this topic. So I'll give you some philosophy on the perspectives. So we're talking about music similarity. And whenever we talk about similarity, it's about differences, but how different is different? That's the question. And if a human expert can perceive that, can machine perceive the same? And the broad perspectives of this research is multidisciplinary. First of all, the acoustic signal that we'll work with. Then the psychoacoustics, how we perceive the signal, and of course, neuropsychology, how we cognize and make meaning out of it. And finally, musicology, because after the cognition, we have to map with some concepts. That's the recognition part of it. So basically, we can rephrase the whole topic as follows: strolling through the songbank, developing ways of seeing cross-cultural relationships in music. So music similarity is a very broad topic. It's multidimensional and multi-paradigm. The dimensions can be timbral, rhythmic, melody, lyrics, and at relevant time scales. Most importantly, it can be a song level, a phrase level, or even at a note level. So let me give you an example. So if I play this excerpt. And here we go with the second. And then we go for the third. So the question is, which is similar to what? A to B, B to C, A to C? The answer is, it depends. A is similar to B according to the melody or the scale, and A is similar to C with respect to the instrumentation, or so to say, the timbre of the song. So this study will be only talking about timbral similarity on the timescale of musical passage. So we have chunked out from musical pieces. I'll come to the details as we go along. And the goal, as I already told, is to make the archival tool for transmitting and understanding the culture, new ways of browsing large collections of music, gather deeper insights on cross-cultural relationships, and create computer applications for mobile devices that enable users to perform, learn, and become encultured in aspects of the music. And I think in the contemporary pandemic outbreak, this is very relevant, the computer applications. Jokes apart, let's go on. So now I'll talk about the corpora and the audio processing. It includes the database, feature extraction, and statistical modeling of the songs. So our core research corpora is, as we call, is the NYUAD Music Compendium. It's music from the region. It has broadly two regions. One is the Arab Mashriq, which is colored as this one, rather highlighted. It's a 500 hours of field recordings comprising present-day countries from different MENA region countries like Egypt, Lebanon, Syria, Palestine, Jordan, Iraq, and also covers parts of South India. And the other one is Eisenberg collection. It's collected by Professor Andrew Eisenberg. It's 170 hours of Swahili Tarab from the East African coast of Zanzibar. And as you can see here, so we have also archived in the true sense of the term this collection. And the model we talk about are a mix of deterministic and probabilistic models. So the very traditional feature like MFCCs are used. We also use PCA to reduce the dimensionality. We use deep stacked autoencoders, the neural networks from the log magnitude spectrum, and finally do a k-means clustering on these features at the high dimensional space, not as the audio, but the reduced one as we did the feature extraction, but finally plot them in a Disney on a 2D or 3D plane for visualization. So that's the outcome. It's a dashboard application. I'll give a demo later. And a VR. That's the core part of this conference. And the idea is to interact and explore the corpus by navigating through the 2D similarity space, where we can hover over different points in the space and listen to the corresponding music excerpts, do a bunch of qualitative evaluation, have statistics, which can aid to different fields of research in diverse fields. And the implementation details, just for completeness, these are the libraries and configurations. So for feature extraction, we have 15-second clips extracted from middle of each audio. And Python's Librosa library is used for extracting these features. And for dimensionality reduction, we use combination of PCA, autoencoders, and Disney to bring it down to 2 or 3 dimensions. And k-means is performed on the original dimensions to cluster into 2 or 6, but I'll take about why is 2 and 6 interesting to us. And for plotting, we have used bokeh and plotly that are very efficient, and they are color-coded, very easy to appreciate for any kind of audience. And also custom JS and D3JS callbacks for interactive part of it. Now let's talk about some tuning, hyperparameters, and qualitative evaluation. So as I told, it's a k-means clustering, but the data-driven way to find the number of clusters. So what is the k in k-means is the most interesting question. So as we have these 2 labels in the metadata, the Arab Mashriq and the Eisenberg, so we of course start with 2 clusters, but we know that it's not possible because first off, the data set is not so much balanced and it's not represented. So there are intra-cluster similarity within the bigger Arab Mashriq collection. So we kept on increasing the number of clusters with some optimization technique until we were satisfied, okay, now this captures the diversity in a comprehensive way. And that is found to be 6 number of clusters. And these plots are for MFCCs for about 2000 songs. And we also do different configurations. So we use PCA, MFCC, autoencoder, and also we use some chroma, constant Q, transform, and tempogram. And these are the 6 cluster outputs of them. I'm not going into the details of each one, but I'm getting into the point that's relevant to this discussion. Now for evaluation, we need to evaluate and have inferences from expert listening. So this is principally qualitative. So we have found these different clusters as we have highlighted or encircled through black points, contours. So there are different identifiable regions by the experts. So one of them is the modern electronic and pop Arab music. Some of them are modern contemporary and classical Arab experts. Some are Persian, or some are with some very specific instrumentations. And this will be very clear when I give a demonstration. And finally, inferring. So this Disney space, as we all know, this is very fuzzy and we can't interpret the dimensions. But this is one of our contributions, as we disclaim, that we wanted to interpret one of the dimensions. And this is one of them. So this is the plotted intensity. It's the average frame-wise intensity. And these are the corresponding points from the clustering. And as we can see, there is a linear trend or say gradient from left to right. And this says there is one linear dimension, at least the x-axis in this plot, we can say. This can be from different effects, but it can also have a meaning. So that's the next thing. Is it a confound or a trend? That's the way forward. So this is to show that this is not incidental. So for each feature and each kind of clustering configuration, we have this linear pattern trend going on. And that said that, so it means that there is a linear trend in one of the dimensions and its intensity. It can also owe to the quality of recording, because these collections were recorded in diverse time instances. And if that is the case, there are two way outs. One is to go and normalize them with respect to this energy and then recluster to find more meaningful results. Or if this is indeed a case and we are deciding to accept that this is the confound for the time lapse, then try to reverse engineer and find the other dimension to have more insights. And this is the technical research part that is still going on in this project. And here I come to the visualization. So there are two aspects. One is the dashboard and other the viewer. So this is how the dashboard application looks. So this is an interactive interface for listening. And as you can see, we can encircle a region and we can get the statistics of all the artists. And this also says a lot of things. So let me go into the visualizations as is. So yes, here is the bokeh plot for MFCC features with two clusters, as I can see. And what we can do is, first of all, we can go and hover over them to listen to the recording. Go somewhere else. The collection, and let's go to the other color. So what does this space mean? So it means that these closely spaced points here should sound similar timbrally, so should use the same kind of instrument. So let's verify that here. These are the same artist recording, and that is also can be verified if we select this region. We can see here there is only one artist everywhere. So this is the same artist playing, so the clustering has done its job correctly. But if we go to some other region, there see the diversity of the artists. So there are so many artists in the statistics. And likewise, we can go to the 6 clusters for the same MSCC features. So you can see the clusters are subdivided within itself. And then for the autoencoder feature, this is how the 2 clusters look and the 6 clusters look. And also we have plotted in 3D, which is, we can rotate it, but still it's not very clear, the spatial distribution. So that gave us the motivation to explore further into the VR space, the 3D rendition. And doing an immersive experience of this listening. So that brought us to VR space for music similarity, and here are a couple of screenshots. I'll give a video demonstration very soon. So we use Unreal Engine 4 as the development environment. We use the CSV data from the clustering output and use them as audio spheres in specific coordinates. And the spheres could be viewed as stars, and the space background has been picked. This is a mere choice by us. And these are simple movements and point and click control mechanics so that everyone can go and have that experience, and it's very intuitive by itself. And for audio streaming, we have used Stream Audio Specialization plugin through UE4. And it does binaural rendering of the audio in real time based on the head rotation and location. So if you move your heads or if you go forward, you really feel the specialization of the audio. And this also traces users' distance to audio source and adjusts the loudness. So there are some research going on in this space. And the device is the Oculus Quest, an all-in-one device that doesn't require a high-end PC to run applications. And also inside-out tracking doesn't need stationary beacons are not needed. It's small size and great controllers and easy to use. That's the most important part. Let's get going to the demonstration. So as I had said, strolling through the songbank. So here's our collaborator Leo, and he's demonstrating the space. Here we go.
This is our welcome window. You can read the tutorial here. You can walk around, fly around in this virtual space by using the thumbstick on the right controller. To select any sphere, just point at it and pull the right trigger. As you may hear, the sound is spatialized. Pull the left trigger to stop audio. You can see we have spheres of different colors. The same color means that the audio clips are somehow similar in their sound. We also have what's called the bird eye view. By pressing the right thumbstick, you can teleport to this location and appreciate the whole scenery from a distance. Press again to return. We also have the predefined path. By pressing A on the right thumbstick, you'll be dragged to a point to listen the manually selected sphere. Press A again to continue on this path. These spheres are selected by us to particularly show you the difference between the colors. And then we return to the beginning.
So yeah, this is it. And to conclude, we want to tell something about the significance in sonic digital humanities applications that the MaSC goals to work with. So we have developed audio analysis and machine learning tools capable of understanding the music from the region. As you can see, we are from Abu Dhabi in the MENA region, Gulf. Creation of a digital corpus for regional music involving both existing and original recordings. Then developing generative music applications having educational goals in mind that we are currently doing in different musical attributes like rhythm, melody. And study effects of rhythm and melody, as I just told, to better understand the music similarity space from different perspectives, and also maybe try to find if there is any coupled effect. And again, coming back, this was a work to combine data and knowledge-driven approaches. And rather than trying to achieve a statistically robust computational model, we used existing technologies and adapted them to develop tools for empirical studies on ethnomusicology. We advocate potential of technology towards music appreciation and engagement for the common mass. And down the line, we want to find appropriate metadata descriptions of genre and structural categorization of these music traditions using domain knowledge expertise. And here I do acknowledge IEEE VR 2020 SIVE workshop. And virtually, it's in reality, it's a virtual conference of virtual reality. And also we acknowledge the NYU Abu Dhabi project and our collaborators, and thank you. That's it.